Hello everyone and welcome to Algebra 2. This is section 5.2, Properties of Rational Exponents and Radicals. Remember that a rational number is anything that can be written as a ratio, or more simply, a fraction. So even 3 is considered a rational number because it can be written as 3 over 1. But mostly, what's going to happen in this section is you're going to take all the rules that you've already learned, you already understand, and we're going to do the exact same thing, but with fractional exponents. So it's going to feel a lot harder. This is often one of people's most challenging sections of the year. So there are examples of each definition here, but I'm just going to jump straight into my own examples so that I can show you how to do these. So if you had 7 to the third times 7 squared, I think I could put that on a quiz and every single person would get it right. You add them because 7 times 7 times 7, and then 2 more 7s can be represented by 7 to the 5th. But this is easy to see how it works. In this case, you're not going to lay that out the same, so you have to know the rule. And that is when you're multiplying like bases, you add their exponents. Well, how do you add 1/4 plus 1/2? You have to get a common denominator. So I'm going to change that 1/2 to 2/4. And then I have 3/4. So this is 7 to the 3/4. The next rule is that if you're raising a power to a power, you multiply them. And I'm not going to go through them all the way I did with this 7, but we are still going to multiply our fractions. So 1/2 times 2. Remember, when you're trying to multiply a fraction by a whole number, it's easiest to make the whole number into a fraction, so you can do numerator times numerator and denominator times denominator. So 1/2 times 2 is 1, so this becomes 6. And then 1/3 times 2, I'm not going to keep doing this, but I'm going to do it for at least a little while to make sure you got it. Change my whole number into a fraction, numerator times numerator, denominator times denominator, 4 to the 2/3. Now these are not like bases, so this is the answer. You cannot simplify that anymore. Number 3, when you have a power to a power, you multiply the exponents. 5 times -1/5 is -1, and 5 times -1/5 again is also -1. These are negative exponents, which means they can be moved to the bottom and be made positive exponents, and this can be rewritten as 1/12. When you have two bases that are being divided, you subtract their exponents. So 1 minus 1/3, you have to get a common denominator. 3/3 minus 1/3 is 2/3. So this becomes 5 to the 2/3. When you have a power to a power, you multiply their exponents. So we have 1/3 times 2, which is 2/3, and then again 1/3 times 2, which is 2/3. Now, since these have the same exponent, we could write them as a single fraction and raise the whole thing to the 2/3. And this would make it simpler because 42 is divisible by 7. So we can write this as 7 to the 2/3. There are some extra examples which I usually use in class for the people that are working more slowly. I have time to go around and help them, and other people can get some extra practice. I am going to write down the answers if you would like to try them on your own, but of course I am going to do them for you, but there are the 4 answers. So these have like bases, which means I'm going to add their exponents. This is 3/4 plus 1/2. I'm going to change that to 2/4, and that gives me 2 to the 5/4. These have like bases, so I'm going to subtract their exponents. This is a 1, 3 to the 1, So I'm going to make it 4/4. That way I can subtract. These, I'm going to do this one differently than I did this one. You're allowed to simplify first. So this is 20/5. They are both to the 1/2, and then to the third. Or you can do it the same way we did number 5. But if you do it first, then you'll get 4 to the 1/2 to the third. And 4 to the 1/2 is 2. Remember that 1/2 means square root. So the square root of 4 is 2. And then 2 to the third is 8. Now, could you have left it 4 to the 3/2? Absolutely. If you didn't see that it simplified further, in this exercise, you're probably just focusing on the radicals, but this one happened to simplify further. On number 9, I can multiply the exponents because I have a power to a power. 1/3 times 3 is 1. And 1/4 times 3 is 3/4. And this cannot be simplified. You don't need to write the 1. But because they do not have like bases, that is the most you can do. It is not 35 to the 3/4. If they don't have like bases, you can't put them together. If they have like exponents, you can combine them. And if they have like bases, you can combine them. But if they don't have like bases and they don't have like exponents, you can't combine them. So this next section is something that's very familiar to you. You may remember that when we had something like the square root of 20, we broke it down into the portion that was a perfect square and then the portion that wasn't a perfect square so that we could simplify the perfect square and leave the other part underneath the radical. You may recall that I called it parts you can do, breaking it down to parts you can do and parts you can't do. We're going to do that exact same process, but as you can see, we're going to do it with cube roots and 4th roots. So before we do that, I did make a little chart for you. I believe I made it the other day as well, but you can screenshot this if you need to. But really what you need to do is have these numbers in your head. They need to be familiar to you. So on this first one, I'm going to use this product property backwards. So we're starting with 2 separate radicals that have the same root, and we're going to put them together under a single radical. I can only do it because they're both cubes. That gives me the cube root of 216, which hopefully looks a little familiar to you. Sure enough, it is a perfect cube for 6, and so this simply is 6. The next one, these are both perfect 4th powers, not perfect, just both 4th roots, so I can put them together. 27 times 3 is 81. And again, I look on my chart, I think 81 is somewhere. 81's right there. And it is a perfect 4th root. The answer would be 3. On the next one, we're going to use the quotient property. These are both 4th roots, so I can put them together as a single root. 80 divided by 5 is 16. And I won't keep going back and forth, but if you look on your chart, the 4th root of 16 is 2. These are both cube roots, so I can put them together as a single cube root. 250 divided by 2 is 125. And that is also a perfect cube. So I get an answer of 5. Obviously, they're not all going to work out that way. So let's do some that don't. So 135 is not a perfect cube. So I'm going to go back and I'm going to look at these numbers, 1, 8, 27, 64, 125, and 216, and ask myself, do any of these look like they go into 135? Well, something like 8 is not my best choice. 1, 8, 27, 64. But I look at the 27 and I say, that might go into it. So I check it on my calculator, and sure enough, 27 does go into 135 5 times. So now I've broken it down into a part that I can do. The cube root of 27 is 3. and a part that I can't. Don't forget to write that little cube there. It's not a square root, it's a cube root. So we're breaking down into parts we can do and parts we can't, but this will only be an easy task if you know your cubes. So hopefully I'm making myself clear. This chart is going to be huge for you. Cube root of 104. This time I don't try 27. I think 27 doesn't sound like it's going to go into 104, but 8 might. So I tried on my calculator, and sure enough, 8 does go into 104 13 times. So the cube root of 8 is 2. That's the part that I can do, and now the part that I can't do. The good news is, while you may not get it on your first try, there's only so many numbers that you're going to have to try. That's 4 cubed. 5 cubed is 125. I'm already over 104. So the most numbers that you would have had to try, even if you're bad at predicting what will go into 104, would have been 3 numbers. Okay, these next two are especially challenging. Because what I don't want to do, even though they're both fifth roots, is I don't want to put them together. That's not going to help me. Instead, I want to rationalize the denominator. Now, you may remember that if you had something like 1 over the square root of 2, we rationalize the denominator by multiplying by the square root of 2 over the square root of 2, because then we had the square root of 2 times the square root of 2, which was 4, and the square root of 4 is just 2. But that's because this gave you the square root of 2 squared. These two numbers matched. So in this case, I can't just multiply by another fifth root of 8. If I multiply the top and the bottom by the fifth root of 8, then I will have the fifth root of 64. But that is not on my list. Fifth power, it goes from 32 to 243. So it's not there. So what I want to do instead is look at my list of fifth powers, 1 to the 5th, 2 to the 5th, 3 to the 5th, 243, and think, can I make 8 into any of these numbers? Well, I can. I can make 8 into 32 by adding a 4. So what I am going to do is multiply the top and the bottom by the fifth root of 4. On the top, because they have like roots, I can multiply them together. Fifth root of 28, 7 times 4. And on the bottom, I get the fifth root of 32. I've made it into a perfect fifth root, so that I can just write it as 2, which is what I need because I'm not allowed to have a radical in the denominator. So number 8 has an extra step because I don't want to start with it both underneath the radical. I'm going to move this one out. And now I need to look at my list of perfect fourth powers. So notice I'm not going to go back to the chart this time. I'm just going to make one real quick. 1 to the 4th, 2 to the 4th, 3 to the 4th, 4 to the 4th, 5 to the 4th, 625. So if you're wondering how I got that, literally 5 to the 4th, 5 times 5 times 5 times 5. And I asked myself, can I make a 5 into any of these numbers? Well, 5 doesn't go into 16 or 81 or 256. I'm going to have to go all the way up to this. So how do I get that to happen? 5 times what? 125. I just realized I put an equal to sign there. It's just a multiplication. So the fourth root of 125. And I picked that because I need to make this into a perfect fourth root. And I chose 625. So now on the top, I don't have anything helpful, but that's okay. I get 375. But on the bottom, I get the fourth root of 625, which is a perfect fourth power. It is 5. And the top can just stay the same. A little bit tricky. Hope you got it. There'll be plenty of homework to practice it on. On number 9, we can't just multiply. We can't do what we just did. We can't just multiply by the square root of 3 and the square root of 3. That will get rid of this. But then when you distribute it, you'll have 5 square roots of 3. So you didn't get rid of the radical in the denominator. So this is another special one. We're going to multiply the top and the bottom by the conjugate. So we've studied conjugates before. Conjugates are when you have a binomial where the terms are the same but the sign is opposite. And you may remember that the reason that conjugates are so awesome is because their inners and their outers cancel, and that's what will get rid of your square root. So when you're doing your FOIL, you get first times the first, outer is negative 5 square roots of 3, inner is 5 square roots of 3, but positive, and then the last times the last is negative 3. Square root of 3 times the square root of 3 is the square root of 9, which is just 3. So it doesn't help us much on the top. We are still going to have a radical, but keep going with higher level math, and you'll find out why we do that. And on the bottom, these cancel, and you get 22. Let's try another one of those. Number 6. So when you see a binomial, which means 2 terms, I'm going to multiply by the conjugate, which means the terms are the same, but the sign is opposite. On the top, I get 18 plus 3 square roots of 2. And on the bottom, I get the first times the first. I'm not going to write inners and outers this time. The whole point of a conjugate is that they will always cancel, so you shouldn't have to write them. Minus, and the square root of 2 times the square root of 2 is just 2 every time. Okay, so I realized that we only did 2 like that, but we have so many other types of problems to try. So moving on to yet another kind of problem. So we're going to break this one down into parts we can do and parts we can't, but it's a 5th power. So I just want you to look at each of them individually. So you can't take the 5th root of 4. So that's going to go in my parts I can't do. A to the 8th, I'm going to put 5 of the a's here, and I'm going to put 3 of them here, because I can simplify the 5th root of a to the 5th. It's just going to be a. How many of the b's, though? Do you know? So I can do 10 of the b's, because there's 2 ways to think about this. One is that if you have the 5th root of b to the 5th, that would definitely be b. So think of it as I have the 5th root of b to the 5th twice. And then the 5th root of this b is b, the 5th root of this b is b. Nobody would go through all this. But this is going to simplify to b to the 10th. Or another way to think about it is to change it to a fractional exponent. If you change it to a fractional exponent, the 10 gets to stay the exponent, but the root becomes the denominator. And you can see that that's going to simplify. So this definitely goes in my part that I can't do. But the other 4 b's, if you were to change it to a fractional exponent, can't be simplified. So those 4 have to stay in the part that I can't do pile. And then of the c's, all 5 c's can be simplified, and there's no c's left here. So my final answer is going to be, when I simplify this, I'm going to get a, b squared, c, 5th roots of 4a cubed b to the 4th. So we're separating it into parts we can do and parts we can't. I guess I'll go a little bit out of order here. I think I'll just scoot over to 15 and do the same thing. So if I'm taking the 4th root of x to the 8th, I can make that x squared. You can think of it as a fractional exponent. The 8 gets to stay an exponent and the 4 becomes a root. Or you can think of it as the 4th root of x squared times x squared times x squared times x squared. I have 4x squareds, so the fourth root is x squared. Lots of different ways to think about it. I don't know which way is working for you. But the fourth root of y to the fourth is just y. Moving up, the cube root of 27 is a perfect cube. And the cube root of q to the ninth is q to the third. Again, two ways to think about it. You can change it to a fractional exponent, or you can think to yourself, okay, I need three identical things. So q to the third, q to the third, q to the third. It doesn't matter to me how you think about it, as long as you're able to get the right answer. Number 13, much harder now. So break it down into smaller pieces. Just do the number first. If all the rest of that wasn't there and you just had 14 over 2, what would you write? You'd write 7. That wasn't so bad, right? And then just look at the x's. So the x's are just x over x to the 3/4. Again, that's a problem that you can do. So this is 1, so I'm going to change it to 4/4 minus 3/4 is 1/4. Now I look at the y's. Oh, there only is one y, so I don't have to do anything with that. And there's only one z, but it's negative. So remember that a negative on the bottom is a positive on the top. So z to the 6. So the reason that this section is so challenging is look at this page alone. We did conjugates. We did breaking it down into parts we can do and we can't. We did negative exponents, fractional exponents. These examples aren't even all the same. It's not like you learn how to do one and you can do all of them. They're all slightly different and very, very challenging. Okay, last two. If you would like to try it on your own, you can, and then skip forward to the answer. But now we are going to, actually not equals, I need to multiply to get rid of that radical in the bottom. So how many more y's do I need to make something that I can simplify? I just need one more, because that would give me y to the 9th. So the cube root of y to the 9th, you can think about it as a fractional exponent, is going to give you y to the 3rd. So I have x cube roots of y over y to the 3rd. Just as an alternative way to do this problem, some people prefer to change it to a fractional exponent. They make it 8/3, and then it's very easy for them to see how many more thirds do I need? I need 1/3. So then they have x y to the 1/3 over y. This is also a valid method and a good alternative. Last one of this type. So again, do them one at a time. Don't let yourself be overwhelmed. The 6 over the 3 make 2. The x over the x to the 1/2, you're going to subtract the exponents, but you need like exponents. So this is 2 over 2 over 1 over 2 is x to the 1/2. Now you can do the y's. Y to the 3/4 over y to the 1/2. I need to subtract them, which some of you can do in your head. Maybe your fraction skills are strong, but if they're not, you can get a common denominator, and then you can see that it's y to the 1/4. There's nothing left in the denominator, but we don't write 0. It's a 1. And so my final answer is 2 x to the 1/2, y to the 1/4. You're doing great. Thanks for hanging in there. I realize that this is really tricky stuff. So for as tricky as all this is, this next part is actually where people make their biggest mistakes. So number one, super easy. You have 1/4 root of 10, You add 7 more fourth roots of 10, you have 8 fourth roots of 10. Everybody gets these. You have 2 8 to the 1/5. You add 10 more 8 to the 1/5. You get 12 8 to the 1/5. Everybody gets these. But then this is where you need to watch out. Watch out. This is where everybody goes wrong. This is not the cube root of 52. Am I making myself loud and clear? Literally, for how complicated I think all of this is, this eventually people get right. They have to practice a lot, but they get it right. This kills me right to the end. Even seniors in calculus do this wrong. You cannot combine unlike radicals. You have to make them the same if you want to attempt to combine them. So I break this down into parts I can do and parts I can't do. And now this is 3 cube roots of 2 minus 1 cube root of 2. You don't really need the 1, I'm just trying to help you out, which gives you 2 cube roots of 2. That's how you do it. If you would like, you could try the next several on your own. I will put the answers here for you, but make sure you show your work. 2z cube roots of 2z squared will be the answer. This one will be 2w squared square roots of w. It's not hard. It's just people don't want to do the work. They just add them. And you can't do that. Okay, so number 4. They don't have like radicals. So I break this one down into a part I can do. Cube root of 8 is a known cube root, and cube root of 5. So now I have the cube root of 5 plus 2 cube roots of 5. And my final answer is 3 cube roots of 5. The next one does have a like radical. I have 5 square roots of y and 6 square roots of y. That gives me 11 square roots of y. So you'll get a couple easy ones in there. Okay, on this next one, it's looking a little cluttered. I'm going to take away my extra answers now that I have them. The next one is, I'm going to break this down. So I can do the cube root of z cubed. I cannot do the cube root of 2 and the other 2 z's. This one has a z on the outside. For cube roots, I can do 27, but not z squared. I am left with 2. 27 times 2 made the 54, and the z squared. This one simplifies to 12z, and this one 2z squared. This one simplifies to z3, which that's a little awkward to write, so I'm going to write it as 3z, even though I'm reversing them. And I realize that that's annoying to have a 3 next to a z. And then also cube roots of 2z squared. And notice that the coefficient is the only thing that's ever going to change. You need to have like terms. So see all of that? Z cube roots of 2z squared, z cube roots of 2z squared gives us, I have 12 minus 3 is 9. Z cube roots of 2z squared. And that's the answer. Last one. This is a square root. So 9 is a perfect square, and so is w to the 4th, but not the last w. This is also a square root. So w squared is a perfect root, perfect square, and w. This gives me 3w squared square roots of w, and this gives me w times w square roots of w, 3w square roots of w, minus w squared, square roots of w. The coefficient here, even though you can't see it, is a 1. And again, as long as everything other than the coefficient is the same, then you can combine like terms. So I have 2 w squared, square roots of w. So like I said, watch out. Even though this entire section is challenging, this is definitely the most missed question. All right, last section. You're almost there. You're doing a great job. If the directions do not say assume all variables are positive, then you must consider the case where the variable is negative by adding absolute value notation. So on these last ones, we're just assuming that everything's positive, just because you had enough to think about already. But now, if I just give you an example, and I don't say that it's positive, you're going to have to add some absolute value. Here's why. Let's say you had the square root of x squared. You might look at that and just say x. But really? Are you sure? So let's say that x is equal to 3. Then the square root of 3 squared is 9. Square root of 9 is 3. That totally worked. But what if x is negative 3? The square root of negative 3 squared is the square root of 9, which is 3. Did it come out? Was the square root of x squared back to x? No, it wasn't. It was back to positive x. So the technical definition is this. The square root of x squared is the absolute value of x. So when I do this problem, I'm going to say the cube root of 64 is 4, and the cube root of y to the 6, I can change it to a fractional exponent if that helps you. Or you can think y to the 6 is y squared, y squared, y squared. I have 3 of them. I'm trying to do cube root, so y squared, whichever way makes the most sense to you and gets you the answer. Now with a cube root, do you have to worry about plus or minus? Absolutely not. Okay, doesn't matter for cube root. It's just for square root and fourth roots that you'll have to worry about it, which of course we're about to do now. So the fourth root of x to the fourth is x. But if x was a negative number, once you raised it to the fourth, that would make it positive. And then when you take the fourth root, it would still be positive. So it's always going to come out to be positive. So I need to write the absolute value of x. Y to the eighth, fourth root, would be y squared. You can either think of that as changing it to a fractional exponent, or y squared, y squared, y squared, y squared. When you do the fourth root of 4 identical things, it's one of them. Now this one doesn't need the absolute value because when you square something, it's already going to be positive. So that one's been done enough. The next one's a cube root. Does it need the absolute value? No. Okay. You only need to worry about absolute value when it's positive exponent. Only need to worry about absolute value when the root, oh, did I say positive? When the root is even. So this is odd. You don't have to worry about it at all. The cube root of 27 is 3. The cube root of d to the 12th is d to the 4th. And the last one, this is even, so I am going to have to worry about it. The fourth root of x to the 4th is x. But like I said, if you started with a negative, once you raised it to the 4th, it would become positive. And then when you took the 4th root, it would still be positive. So to account for that, we go like this. And the 4th root of y to the 16 is y to the 4th. And in this case, it's not necessary because y to the 4th is always going to come out to be positive. Okay, so if you go back and look, I did say right at the beginning of this that all variables, assume all variables are positive, that is going to be the lion's share of your work. But if they don't say that, if you don't see that, then you need to recognize that you'll have to do this thing with the absolute value. All right, really tough lesson. I can't stress enough. Make sure you don't just do the homework and get answers, but that you understand it and that you come and ask for help if you need it. That was section 5.2. Have a great day.